seminars of the fall semester. And I'd like to welcome Xiang Cheng to our departmental seminar. He's a relatively new professor. He started here in the Department of Chemical Engineering and Material Science last fall, so he's been here a year. He got his undergraduate degree in physics at Peking University. He had his PhD in physics at the University of Chicago. And he recently completed a postdoc at Cornell University in material science. Xiang's research is sort of spans across colloidal dynamics and also granular physics. The colloidal stuff, which he won't be talking about today, is also very interesting. There's the rheology of colloidal particles, trying to understand shear thinning and shear thickening at the particle scale, so the dynamics of the particle scale. And if you're interested in that aspect of his research, there's a Science article that was published, that he published on it about 2 years ago. Today he'll talk about impact response of granular materials, cratering, and related problems, including problems related to Martian dynamics. So it seems like it'll be a really exciting lecture. Thanks for coming, and let's welcome Professor Xiang.
Great. Thank you. Thanks for the great introduction. Actually, I'm really new here, so this is actually my first time to give a talk in civil engineering department. So my group, as what Kimberly said, we study motion and physics of particles. This particle can include centimeter, millimeter size big particles, like granular particles, all the way down to micrometer or nanometer size colloid and nano suspensions. So again, in my talk today, I'm going to focus on our research on granular materials. So I'm going to show you two simple but very interesting experiments to demonstrate the unique feature of granular flows. And again, we have a really big part of our research on colloid suspensions. So if you're interested in that, I can tell you about that after my talk. Again, I like this quote here from Aristotle. He said that to be ignorant of motion is to be ignorant of nature. That's why we care about the motions of particles. And ironically, he's the guy who ignores a lot of motions, right? We know he got a lot of things wrong. Anyway, so let me give you some quick introduction. I'm sure that most of the audience here already know what's a granular materials, but I see some of our colleagues from chemistry and material science, they may know as much as you know, so let me give you some quick introduction. So granular materials basically is a large collection of big particles, right? And you can see granular materials everywhere in our daily life and in nature. So I just put some very simple example here, a pair of hazelnut, that's clearly granular materials. To a larger scale, surface of desert, surface of Mars, that's clearly granular matter. And to an even larger scale, actually, the ring of Saturn, that's a good example of granular matter. Under influence of gravity, those big marbles and rocks, they keep colliding with each other. So the whole ring actually form a good model for granular gas. And since granular materials is really, I think, the second abundant materials on Earth besides water, so it has a really broad application in environmental science, in agriculture, in industry. Actually, I talked to people from Dow Chemistry. 90% of their product was granular materials, either as a raw materials at the beginning or was an end product. So it's very important for us to understand and to know how to handle granular materials. Unfortunately, we are not at that stage yet. So it's estimated actually 40% of our industry plan, the capacity of our industry plants is wasted because of a problem of granular materials. And this number is much smaller if we have plant handling liquid form of matter. So from fundamental scientific point of view, actually granular matter provides really interesting physics. It shows unique behavior that's different from standard form of matter. So I just give you two examples here. Above yield stress, actually granular materials can form this flow behavior. But it just, no need to carefully look at this picture. You can already pick up that this flow behavior is completely different from Newtonian fluid behavior. You have fluid flows, usually you have linear velocity profile. But here you can see flow, this avalanche flow only confined near the top surface. So to show different behavior. And near the yield stress, granular flow can be stopped. You have this jamming transition. And right now in the granular physics field, people generally believe that the jamming behavior of these big particles has a deep link with the glass transition of molecular liquid. So hopefully by understanding the behavior of jamming of big particles, you can have a better understanding of this long-time mystery of glass transition. So part of my research also working on this area, but unfortunately I don't have time to talk about that. So another important feature we should bring out here is that the temperature plays no role for these materials, because the energy you need to move one particle going around is way higher than KT at room temperature. Essentially, you can say granular materials are zero temperature materials. They always fall out of equilibrium. That's why we cannot apply the well-established equilibrium statistical mechanics to these materials. And that's one reason we don't have good understanding of the behavior of granular matter. But on the other hand, granular materials actually provide a very useful system for a lot of interesting non-equilibrium physics problems. And hopefully, I can convince you in the later of my talk that the two experiments we are doing in my lab actually form a really good analogy to some really exotic physics questions. And that's one reason why I put these two experiments together in my talk. And another reason I put them together is because both experiments show the response of granular materials under impact. When you have really high speed, fast impact, strong impact on granular materials, you can think the granular materials suddenly become liquefied and they can flow. And this experiment actually characterizes what's the flow behavior of granular matter under impact. So let's move to the first part of my talk. This is the first experiment. Again, very simple, but I think very interesting experiment. The first experiment I show you here is a granular impact cratering by liquid drops. Okay? So I'm sure that everyone here is familiar with this phenomenon. You see raindrops splashing in your backyard, on beach. Basically, that's just a liquid drop impact on granular surface. And apparently, this has a lot of application, for example, in agriculture, drip irrigation, that's a liquid drop impact on granular surface. And in environmental science, soil erosion is directly related to raindrop splash on granular particle. And in industry, people use this process actually to suppress dangerous dust. They spray water on the surface of granular bed, make sure that you don't have a lot of dangerous dust. And after we do the experiment, we found this very interesting paper published 2 years ago in Nature. What they found there is actually a fossilized granular stone with this raindrop imprint crater. And the author claimed that those craters are actually from rain activity 3 billion years ago on Earth. And from the size of this crater, they know the terminal velocity of raindrop, and then from that, they can deduce air density on Earth 3 billion years ago. So this is really cool work. But apparently, it's very important for us to understand how the size of crater relates to the impact energy. It's still unknown question. So that's a part of our research. But before I tell you the detail of the result, I just want to show you 2 really cool high-speed video we took. And this 2 video to show you 3 millimeter water drop hitting on a granular surface composed of 90 micron glass beads. Okay, it's took by a high-speed video. First one is at 8,000 frames per second. Second one is 10,000 frames per second. And the size of the water here is the typical size of a raindrop. So if you're raining outside, this is roughly the size of the raindrop you can get. So the first video, the live video here, I'm going to release my drop 5 centimeters above my granular bed. So that means that the impact energy of this bed is impact energy of this liquid drop is small. So as you can see here, this is what happens. When the drop impact on the bed is spread out, and then because surface tension, it will come back. When it's come back, it accumulates a layer of particle on the surface of this bed. And then this drop can even bounce off the surface, and then at the end will fall at the center of the crater. And the whole movie here is about 100 milliseconds. If you wait longer time, let's say on time scale of a second, all the water here will drain into the bed. You get a really fascinating liquid drop imprint structure. I'm going to show you that later. The next movie I'm going to show you here is what we release a drop at 1.5 meter above the bed. So this is really close to, similar to raindrop splash on the surface. This is what happens. When the drop impact on the surface is violently splash out, and then you generate a lot of secondary droplets, and the whole thing mixes up with a lot of granular particles and form this pancake shape and fall flat on the surface of the granular bed. I want to mention, I forgot to say that all the movie here actually taken by 3 undergrad students in my group. This is really, everything I tell you here about this granular impact cratering of liquid drop is a new project that I initiated after I come here. So the first few days when I was in my office, they just knocked my door saying that, Professor Cheng, can we do some interesting research on granular matter? I said, yes, let's do this together. So it's still an ongoing project, but I think we found some really interesting results over last year that I want to share with you here. Okay? So the thing we care about is we want to understand, we'll characterize what's the morphology of liquid drop imprint. Okay? How this shape of the imprint depends on, for example, impact energy, drop size, particle property, liquid property, all different key control parameters. And we want to understand this morphology based on the dynamics I show you in my previous slide. So here I show you a picture of liquid drop imprint on granular surface. This is a typical imprint you get when the impact energy is on the intermediate impact energy. It's not really high impact energy. And there are two features you can immediately see from this imprint. One is the size of this crater, and another is the size of this granular residue at the center of the crater. So I'm going to talk about those two features separately. So let's look at the size of the crater first. So before I tell you the liquid drop impact craters, I want to say something about solid sphere impact crater. The reason are two. First of all, there are a lot of research in granular physics. They study different aspects of a granular impact cratering by solid ball. So they have granular bed, the zero ball of different size, different shape, try to see how big of the crater and what's the cratering pore size. And another reason is that I'm going to introduce a very simple scaling law here that I'm going to use later in my talk. So let's look at this structure here. I drew a solid ball, in this case a stainless steel ball, on the surface of granular surface, and we'll create a crater like this. Actually, the size of the crater follow a very simple scaling with the impact energy. Let me show you here. So let's say E here is my impact energy, the impact energy of my ball. This impact energy is used to create a crater of volume V. And when you create this crater, you have to move all the sand in the crater outside the crater. The vertical distance you move is roughly on order of the depth of the crater, right? I have to move the grain against the gravitational potential of each grain. And if you assume the depth of the crater is linearly proportional to the size of the crater, then you know the volume of the crater should be the size of the crater to a cube. Very simple geometry, right? Now you can put everything together. D here give you 1 D crater, and the volume here give you D crater to a cube. Altogether, you know the energy should go to D to the 4th power. If you inverted that, you see the size of the crater should go to impact energy to a quarter scaling. That's actually what they saw. Here is the symbol here too small. Basically, what I have here is the dimensionless size of the crater as function of the impact energy. You see they follow a really good power law scaling with power at 1/4. Now the question we have here is that what do we have if we replace a solid sphere with a liquid sphere? I want to mention that actually we are not the first group to do that, of course. There are a couple of recent research. You see very recent research here. They also study the same problem. And the result they got there is very controversial. Some of the research saying that, the power law is still a quarter. They just behave like a solid sphere. And they have some argument why. But another research saying that, no, the scaling is totally different. And the reason why they have this controversial result is because the impact energy they explored is very limited. As we know that if you want to study power law scaling, you want to extend the dynamics range as much as you can. So we want to improve that result here. So indeed, in our experiment, we do experiment from the drop deposition regime, where we actually release the drop 1.8 millimeter above the surface, so very close to the surface, you get really small impact energy, all the way to 12-meter height experiment. So we drop a drop from 12-meter high height. And actually, the experiment sounds simple. It's really hard to do because at that high height, your tiny millimeter drop, if there's any flow in your room, it will just go away. You cannot find your drop anywhere. So you have to repeat the experiment many times until you can have a right target location you can do imaging. So as the experiment actually done at SAFO, so they have the really high height building there we can do experiment. So let me show one video here. If I can stop in the middle. So the key thing I want to show you here is that for this 4 millimeter drop, 4.6 millimeter drop, and when it's full from 12-meter high height, actually the drop itself is not spherical anymore because the air drag on the drop is so high, the whole drop will deform into an elliptical shape. If I finish this, you'll see there's a very violent splashing behavior. So this video is taken at 20,000 frames per second. So if you do a simple calculation here, you know that at 12 meter here, the impact velocity of our drop already reached 98 or 99% of the terminal velocity. So we are really in the good shape to detect how the size of the crater changes as function of impact energy. So this is our result. Okay, so here what I show you is the size of the crater as function of impact energy over more than 4 order magnitude in terms of impact energy. This is really drop deposition regime all the way to the terminal velocity regime for different drop size here. The first thing you can see directly is that for all different drop size, they indeed follow a really good power law scaling. And the power here is very weird power is 0.17. This is clearly smaller than quarter scaling, which is for solid sphere impact. Now the question we are facing right now is, why we got this weird power law scaling, how we understand this weird power law scaling. And the second thing is how you make your size of the crater dimensionless. You see that not only the energy dependence, apparently this crater size also depends on your drop. For different drop, you get different size. And also, how about another property like a liquid property and particle size, etc. So the first thing is we want to understand this power. And this is really weird power, actually. You know, we do a lot of thinking, calculation. We don't get this power. And then we just turn to literature. We do a lot of literature search. At the end, this is really a surprising result. We found some literature. This is a review paper in 93, but actually a lot of research is done back to 1960s or 70s. I guess at that time is the Apollo program. People really care about the surface of moon. They try to understand what's the asteroid impact crater size and how does the crater size relate to asteroid impact energy. And this is a really famous scaling law from the planetary science. It's called the Schmidt-Host-Apel scaling. If you look at this Schmidt-Host-Apel scaling, you find that the size of crater actually go as impact velocity to 0.34 power, and you can easily convert this into impact energy. That's give you 0.17 power law scaling. That's exactly the same as what we found here for liquid drop impact crater. And another good thing for here is that they also show us how this size of crater depends on the size of the impactor or size of the projectile. In their case, the size of the asteroid. So we just say, okay, let's apply this full scaling to our result here, see what we got. And we found that if we do the scaling, this is our liquid drop crater, and then we divide by this whole scaling here. Of course, we would replace the size of asteroid with size of a small drop. We replace the density of the asteroid with the density of our small drop, and everything collapses together. All our different drop sizes give us a constant relation, and the constant here is 1.74. Not only that, we do experiment with different particle size, with different liquid. We use methanol, alcohol, the methanol, alcohol, ethylene glycol, water glycerin mixture, and we treat the particle with different chemicals so they have different surface property. We even do experiment at low ambient pressure. All our results follow this scaling relation. So it seems that this scaling relation is really robust. Now the question we can ask, how we can understand this scaling in our experiment. So fortunately, a lot of astrophysics already considered about this. So for asteroid impact cratering, this Schmidt-Host-Apel scaling, actually you can understand that based on simple similarity and dimensional analysis. So this is just saying that the scaling actually is independent of the detailed dynamics. Essentially what you do there is to pick up what's the most important parameter you should consider about in this case, and then you do a dimensional analysis. Actually, undergrad can do that. So this is basically what they understand in asteroid impact cratering. And of course, we can apply this into our case. But this is useful. We got the scaling. But this really doesn't tell us the physical insight of why you have this scaling. Now, the next picture will be much useful from asteroid impact cratering study. So in asteroid impact cratering study, people found that actually 97% of impact energy turn into heat. So it's heat up the asteroid and heat up the surface. Only less than 3% of energy is really used to create a crater. Only less 3% of energy used to increase the kinematic energy of the impact materials. And because of this large energy partitioning, actually you can have power law scaling between this quarter scaling, which I showed before, and this what they call momentum scaling, 0.14. So you have this number between these two. So now I'm going to borrow this idea into our liquid drop impact cratering. So what I'm trying to argue is this. When a liquid drop hitting on the surface is completely different from solid sphere because not all the energy used to create a crater. A lot of energy actually turn into surface energy of the deformed drop. Because drop will deform, that's create more surface, you need more energy to give you the surface energy of the drop. Second of all, a lot of energy actually go to the viscous dissipation of the spreading lamella. So I have this simple assumption. Let's assume that the energy to create a crater actually is only part of the total energy. So F here is what we call energy conversion coefficient. It's a factor smaller than 1. And then the key assumption I'm going to make here is this. So let's assume this energy conversion coefficient is inversely proportional to the surface area of the crater. Why can I have that? My argument is this. When you have a bigger crater, the drop coming in, the drop has to spread more. You create more surface there. So you need more surface to supply the surface energy. Also, because surface area is bigger, the viscous dissipation is bigger. You also need to supply more energy into that source. That's why the energy to use to create a crater actually is smaller. That's why you have this 1/, surface energy dependence, surface area dependence. And because this energy conversion coefficient, we know that this coefficient has to be dimensionless. And the only dimensions, the only surface area can make the whole thing dimensionless is the surface area of your drop. Okay? So this is my assumption here. F should follow this formula. And we don't know whether it's right or wrong, so we will see where this leads to us. So if I have this, then we can apply the energy scaling I showed you before. So the only difference now is that instead of total energy, I say only this part of energy is going to create a crater of V over the distance of D. Okay? Again, I assume that the depth of crater is proportional to the size of crater. Alpha here is a constant, essentially is the aspect ratio of my crater. And if further, I assume my crater has a parabolic shape, which is really good assumption. We can see that from our video. Then you know the volume of a crater should follow this relation. Now we can put everything together. We know how this relates to total impact energy, and now we know the volume of crater, we know the depth of crater. If we put everything together, actually we go back to this Schmidt's whole-cycle scaling. Okay? So that's where this weird 0.17 scaling come from. Actually, we got the size of crater go as impact energy to 1/6 power, which is 0.166, is essentially 0.17. That also give us right scaling on the size of the drops. And there's one more thing that I can predict from this calculation. That is, if I link the prefactor I measured from my experiment to the prefactor I calculate based on the scaling argument, I can find basically the upper limit of the crater aspect ratio. So I know the crater aspect ratio should be around 0.25 plus minus 0.04. So essentially, this is really the upper limit we should have, because essentially when you create a crater, the particle actually will jump higher than D. So that's why I said this is the upper limit. So let's compare that with our measurement. For the depth of the crater, I have to wait until the liquid drop bounces off the surface. Otherwise, I don't know where's the bottom of my crater. When I do that, I can measure D, the depth of crater, and I plot here the aspect ratio. Actually, the aspect ratio is about 0.2. So very close to the simple energy scaling we have from previous slide. But more interesting result is this. I want to compare the shape of my liquid drop impact crater with asteroid impact craters. So what I'm showing here is the depth of the asteroid impact crater as function of the size of the asteroid impact crater. And the result here, again, from literature back to 60s, and this, again, is a review paper. So you can see for Moon crater, Mars crater, and the Mercury crater, they all lining up together. Essentially just tell you that the depth of crater follow a linear relation with the size of the crater. Now you see the unit here is on kilometer scale, so it's really big craters. Now if I extend this line all the way down to millimeter scale, that's our result. So liquid drop crater indeed follow the same self-similar shape as the asteroid impact crater, in spite of the 4-order magnitude difference in length scale here. I also want to point out that this is not generally true for any granular impact cratering process. For example, the well-studied solid sphere impact cratering, actually the aspect ratio is 0.12, is smaller. And on this scale, it looks similar. But if I plot them separately, so this is my liquid drop crater, the solid sphere impact crater. As you can see, the crater actually is much shallower. Okay? Now the question is why asteroid impact crater and raindrop crater show same energy scaling and show similar crater shapes. Of course, the energy scale is totally different, right? We are talking about 18 to 20 order magnitude difference in energy scale. Of course, the physics, dynamics of physics, the physical process there will be different. But still, the result here is really suggestive. We want to ask, what's a possible reason give you this surprising similarity? So we come up with 3 reasons. The first reason is this. People study asteroid impact know that the dimensions number control this process is a Froude number. Froude number essentially compare gravitational energy with the impact energy. For asteroid impact crater, if you just put the size of crater, the velocity of the impact there, you see the range is between 10 to -6 to 10 to -2. If you do the same calculation for liquid drop impact crater, actually, even though the velocity of our impact is smaller, but the size of the impactor is also smaller. Actually, we have pretty good overlap in terms of this dimensions number. The second thing we argue here is this. When the impact happens for asteroid impact, as I showed you before, everything heat up so quick that the impact pressure actually is on 1,000 gigapascal, and the temperature is way above 2,000 C. At that high temperature, nothing is solid, right? Actually, the asteroid is already melt down. Most of them actually is already vaporized. And in that sense, actually, our liquid drop form a really good analogy of what happens there, because this is a liquid at the beginning. And the final thing I can argue here is this. For the asteroid impact crater, when people do the simulation, they simulate the impact surface as a Bingham fluid, which means that fluid with yield stress and show shear thinning behavior. And we know that granular materials actually form a really good model for Bingham liquid. And based on these three arguments, I'm trying to say that actually two processes share some similar mechanism in this too. Okay? So that's my first part, talking about how we understand the size of crater. The next part, I'm going to tell you how we understand the size of a granular residue at the center of the crater. So here is our result. We measure the size of this granular residue as a function of impact energy for different drop size again. You can see the size of granular residue first increase slowly, but above certain transition energy, it's begun to increase very quickly. And the question is why? Let me show you the morphology of the liquid drop imprint first. So at low impact energy, you first have this donut shape. So you have ring and have a hole at the center. If you increase the energy, you see this donut shape, basically the wall here gets thicker and thicker. The granular particle began to fill up the central hole there. And then if you increase the energy close to the transition point, you see this is a full saturated pellet shape. And then at the transition temperature energy, you see this shape become asymmetric. You begin to see these fingers going out. And because this finger actually enlarges the measurements you have on the size of the granular residue. And when you increase the energy more, the size becomes flatter and larger. That's how this increase larger. So we can build up some simple mathematical model to understand this trend. So first of all, remember I showed this video at the beginning of my talk. When the liquid drop hitting on the surface, it will accumulate a layer of particle on its surface. And once it retract back, because the surface area gets smaller and smaller, because we try to retract back to a ball, that means that all the surface particle has to be pushed into the bulk of the liquid marble. And that's why you can have a thick layer of granular particles lining on the surface of a water drop. And when the water drains into the bag, actually that's what you got. You have a wall of particle at the outside, and all the water from the center just drains into the bag. And now you increase the energy more, essentially you're spreading your drop more, you accumulate more particle. When this thing retract back, it pushes more particle toward the center. That's why you can close up the hole at the center. And then eventually, at large enough energy, you accumulate so much particle, when this thing retract back to a sphere, it actually saturates the whole sphere. That's why you can have this solid saturated pellet shape. And now, at the end, you will understand when the energy even higher, you spread more. When this thing retract, you already have a saturated ball at center. Eventually, before the ball can really come back to a spherical shape, the particle will jam the retraction of the drop because come from the capillary retraction. So that's basically the whole idea here. And what I'm going to do now is just mathematics. So very simple idea. You assume that the number of particles entering at the surface of spreading lamella, you should go as a surface area of the crater divided by the cross-section of the beads. And then the total volume of the liquid marble here should be total volume of the drop plus total number of particles. And then you can ask, what's the length of this liquid marble? Very simple. Once you know the volume, you can calculate the effective length diameter of the marble. When the size of the marble is smaller than the capillary length, you know the marble keeps a spherical shape. That means that your granular residue, which is roughly the size of the marble here, should be the same as the diameter of the marble. But if the length of the marble is bigger than capillary length, then you should have a puddle shape. And the thickness of the puddle is on order of the capillary length. Then you can calculate the diameter of the puddle. That's give you the diameter of the granular residue. And actually, our model follow our experimental result well. So all the solid line here is a liquid marble theory we found based on this simple calculation. And now, if we ask what happens at transition point, as I say that when the particle tries to come back with the liquid, it cannot fully, it's already fully saturated the ball at the center. It cannot come back, it will jam the retraction. That's how you get this transition point. What we do is that we assume that at transition point, the volume of the particle reaches the jamming transition of granular materials. We know at the jamming point, the volume fraction of the particle should be 55%. If we have that jamming criteria, we can calculate the transition energy as function of the size of the liquid drop. You see our experimental result and our theoretical calculation fall on top of each other well. So let me summarize the first part of my talk. So the first part, I show you a dynamics of granular impact creating by liquid drops. And from that dynamics, we try to understand the morphology of raindrop imprint. What's the shape of the imprint, how we understand how this relates to impact energy. And the more interesting result is I show you this quantitative similarity between liquid drop impact cratering and asteroid impact cratering. If you believe what I say, actually the raining in your backyard is same as the asteroid impact you found on Earth. So I show this result through some astrophysics. Okay, the conclusion is this. Okay, we don't know because there's 4 order magnitude difference between the two. It's really hard to conclusively say these two are same. But let's say if this is just a coincidence, it's just a coincidence. He said that this is really amazing coincidence. Why? The raindrop splashing is same energy scaling and same shape as asteroid impact crater. Okay, so that's the first part of my talk. The second part, the first part, what I'm showing you here is what happens if you have a liquid drop hitting on the granular surface, how the granular surface responds to that impact. The second one here, I'm going to show you a direct impact. What I'm going to have is a granular jet hitting a solid target. I'm going to see how my granular materials deform. Again, this part of experiment is motivated by a classical fluid mechanics experiment where people study a behavior of a water jet hitting on a solid target. Okay, this is actually a video I took in the kitchen of my house. So what you have here is just a water jet hitting on an aluminum bar here. You see the water jet actually deform into this really thin water film, and they close up at the end, give you this very elegant water bell shape. This actually experiment was first done by Savard in France more than about 200 years ago. So this Savard is the Beer-Savard law in electromagnetism. So if you remember your undergrad physics. So more recently, another French scientist, Christophe Clainet, he really studied the detail of this water bell shape. So then the question we have here is what happens if you have a granular jet hitting on a solid target? What are we going to have? Again, our experiment here is very simple. What we have here is essentially just a glass tube, and we fill the tube with a column of granular particles. We use different granular particles, glass beads, copper beads, rough sand, and we vary the size of our granular particle from really small particle, 50 micron, all the way to 2 millimeter. And then we link this tube to a high pressure tank. And then when you open up the valve, the high pressure gas here will push the sand column and let it accelerate and hit a solid target in front of the tube. By varying the pressure of the tank, you can vary the impact velocity. And another thing we change is the size of the target. We use a bigger target and small target to see what happens. Again, we use a high-speed photography to look what happens. The first video I show you here is I'm going to use a small particle, 100 micron glass beads, and the beads were hitting on a big target. So the size of the target over the size of jet is about 4.5. Okay? So this is what happens. The jet moving out and hitting on a solid target. I want to stop here. You see this amazing phenomenon. The granular particle all concentrate into very thin, almost quasi two-dimensional granular sheets. I don't know if you realize that the particle we have here is a hard sphere particle. They don't have attractive force there. The question is why they don't scatter into all different directions. Why they all concentrate into one plane? Yes?
Which way is gravity?
The gravity is pulling down. So, but the speed here is so high that at this short time scale, the gravity doesn't play any role yet. But if you don't have target, this thing shoot out, you will see the jet actually will bend down because of gravity. This is really amazing phenomenon. You can see there's a really sharp fluid-like plane going out at 90 degrees with respect to the incoming jet direction. And now the next movie I'm showing here is what happens if you have a jet hitting on a small target. So in this case, instead of a 90-degree plane, let me play this a little bit longer, you see this cone structure. And you see the surface of this cone is so thin, it's almost transparent. You can see the target holder inside the cone. Okay, so the big question, of course, we want to ask, where does the fluid-like behavior come from? But I will go to there at the end of my talk. The first thing we can directly measure is how the cone shape changes as a function of the size of target. So I measure basically the half angle of this apex angle. And as you can expect it, when the target is really big, you basically have this plane 90-degree granular sheath coming out. But when the target is small, you begin to see this cone shape. The angle here is smaller than 90 degrees. An interesting result is this shape does not depend on density of the granular particle. We use glass beads and copper beads to give us the same result. And I will tell you why that. And first thing we can do is let's compare this with water bell, right? The elegant water bell shape. For water bell, because they have surface tension, the bell will close up at the end, give you this bell structure. But we can still measure the tangential angle of this bell, right? So Christoph Kleinert, he measured this thing, and he found that the angle actually increased with Weber number. In this case, Weber number depends on velocity. Weber number, again, is a dimensionless number. Compare kinematic energy of jet over surface tension energy of the jet. So sigma here is surface tension energy, surface tension of the liquid. As you can see, when you go to high Weber number limit or high velocity limit, this angle almost saturates. And then what he plotted is this a saturated angle. He called that the angle at a high Weber number limit as function of the size of the target. It shows very similar result as what we found. Large target, you see 90-degree plane. Small target, you see a smaller cone. And when we plot everything together on top of our data, we found that actually our granular data follow exactly the same quantitatively follow the same trend, as water. And now when we think about this question, everything makes sense. Because we can ask, what's the Weber number of granular jet? And as I tell you, our granular particle has no attractive force. So there's no surface tension for our granular jet. If you really calculate the Weber number is almost infinity. That's why you can change your density by changing from glass to copper. The result doesn't change. Because you can change your density by factor of 2, doesn't help you too much because your Weber number is already really big. And this also predicts that indeed the shape of the cone actually does not depend on impact velocity. And we tried that actually no matter what's our impact velocity, as long as the gravity does not play a role yet, we see exactly the same result. Now go to the, also the another thing is that we can do actually we can do some theoretical calculation. You have the constitutive equation for granular jet, and then you can predict what line you have. So there's some, I would say simple but tedious calculation that you can get both sides of this solid lines from our theoretical calculation. The interesting part I want to talk about here is that where does collective fluid-like behavior come from? So our experience tells us that if you have a ping pong ball or you have a basketball, you draw the ball to the wall will just come back. It won't flying out into 90 degrees to give you the plane structure. Apparently, to get this collective fluid behavior, you need a lot of collision between particles. You need a really high number density of particles. They experience many collisions before they flying out. That's how you can get this collective behavior. We can demonstrate this effect by using bigger and bigger particles. So what I'm showing here is that I fix the size of my jet, but I'm using bigger and bigger particle. The first one here is what I show you with my movie. When I use a small particle, you have this really beautiful fluid-like sharp plane. But when I increase the particle size 5 times larger, in this case, I will have a fewer number of particles across the cross-section of my beam. You can see this fluid plane become blurred. You can already see some particle flying out in different angles. Now, if you use really big particle, 2 millimeter particle, in this case, I only have maybe 2 or 3 particles in the cross-section of my beam, I start to see this firework-like pattern. This is really a particle behavior. And we can try to understand that by doing calculation. If you assume that particle only collide once and then flying out, then what we call as a Bowen approximation in quantum mechanics, then you know that the flying out angle should give you sin theta distribution. Actually, our big particle, is at least consistent with this prediction. Now we can calculate when you have a second order scattering, third order scattering, and more scattering, come into your problem, then this y distribution becomes sharper and sharper. At the end, you will get this almost dirt-like function that's give you the fluid-like plane. And in this case, the calculation becomes so involved, actually we resolved to a simulation to see this effect. Now what I'm going to do is show you the most interesting part of this talk. So what I'm going to demonstrate is that this emergent fluid behavior out of discrete the interaction of discrete particle is not unique only for granular materials. Actually, our granular jet form a really good classical analogy to Quark-Gluon Plasma found in RHIC. I guess not a lot of you know RHIC. So RHIC here is a relativistic heavy ion collider at Brookhaven National Lab. They have this huge accelerator. I think the diameter here is about a few kilometers. This accelerator is smaller than what they have in CERN, but it's big enough for them to accelerate the heavy ions like gold or lead to a speed near the speed of light. And then what they do is they let these two heavy ions collide. And because energy is so high, at that high energy, when the two balls smash together, the hundreds of proton neutron in this heavy ion will decompose into quark and gluons. So basically, after collision, you have a soup of Quark-Gluon Plasma. And then after a very short time, the Quark-Gluon Plasma will combine into another particles and then flying out. They put their detector around the collision area, and then they can measure the particle momentum distribution in the antimodal plane. And from that distribution, they claim that Quark-Gluon Plasma is a liquid. Actually, this is a really big physics discovery, I think about 10 years ago. The reason for that is that people know that after a few milliseconds of a Big Bang, our universe actually is a Quark-Gluon Plasma because energy at that time is so high. And this result is showing that our early universe is indeed a soup. It's really a liquid, not a gas. Now I'm going to show you that actually our granular jet form a really good analogy of what happens there. But before that, I need to tell you why they say Quark-Gluon Plasma is liquid. What's the evidence they saw? They saw in their experiment. The big evidence they have is what they call anisotropic flow. Okay, I will tell you what's that. So let's think about a simple situation first. In this drawing, I'm showing you cross-section of two ions, okay, two heavy ions. One ion, I use the solid line to represent that. Let's say this ion moving out of the screen, moving out in z direction, okay? And then I have another ion, which is the dashed line here, moving into negative z direction. And they're going to do this what they call hand-on collision because the center of these two ions are lining up together. And in this case, because the collision area here is symmetric, and the interaction, there's no reason to think of any asymmetry in the interaction, then what you should have is a uniform distribution of particle momentum. That means that if they have detector surrounding this area, they will see equal number of particle momentums along different directions in this antimodal plane. Nothing new, nothing interesting can happen here. But what really interesting is if you have this situation. If you have one heavy ion moving out here, and another ion moving in here, the overlap regime here is not symmetric anymore. You have this almond shape. Only in this area, the two ions will collide. Okay? In this case, by detecting the particle momentum distribution, you will know what's the state of matter inside. How? For example, if your Quark-Gluon Plasma in this area here behave like a particle, I call that ideal gas, then each particle here can still choose any direction randomly. So we will still have uniform distribution of particle momentum because they don't talk to each other. They don't know what's the shape of the whole region. They just choose any direction randomly. Okay? However, if Quark-Gluon Plasma interacts so strong, or you can say collision so many times, the whole regime becomes a liquid. Then what happens is that you can talk the concept of fluid. That means that we can talk about pressure. Of course, pressure at center here is just one value. Pressure outside here is 0. But because the length here along this horizontal direction is shorter, that means that it will have a higher pressure gradient across this direction. Because the pressure difference same, if you have a shorter length, that means you have a higher pressure gradient. This higher pressure gradient along the horizontal direction will push more particle along the horizontal plane. Then you have a larger particle momentum along this direction. And you have a smaller particle momentum along the vertical direction. That's actually what they saw in their detector. They see exactly the same pattern I show you here, and they say the Quark-Gluon Plasma indeed is a liquid. Now the question is, can we repeat the same experiment in our tabletop experiment? Their thing is a few $1 billion experiment. Our thing $10. So can we do that? Okay. The idea is this. First of all, you can treat the target, what I showed you before in the movie, as a mirror. So one jet hitting a target essentially behave like two jets doing hand-on collision. Actually, I do experiment with two jets. They show exactly the same behavior. Now, if we use a cylindrical jet, the jet that I showed you before in my movie, of course, the collision area, it will have a circular shape. And no matter what happens, you have uniform azimuthal distribution of your particles. That's indeed what we saw. Now, if you want to mimic RHIC experiment, you have to generate a collision area which has this elongate shape or non-circular shape. The idea to do that actually is very easy. I already showed you the answer here. What you can have is just have a cylindrical jet. Before it's hitting on target, you put another slot there. When the jet passes through the slot, the cross-section of the beam becomes rectangular shape. And then you let this rectangular shape hitting on target. It behaves like two jets with rectangular shape hit on each other, and the collision area will be non-circular. You will have this shape. And let's see what happens. Okay, so the setup we have here is this. The beam, the granular jet, will moving out of the screen. Okay, I put my camera behind the target, and I want to see what's the distribution of particles and distribution of particle momentum in this azimuthal plane. The only difference between this experiment and previous experiment is this. Instead of a circular jet, I'll have a jet with a cross-section like this, with a rectangular cross-section. So I will have a short axis along y direction, a long axis along the horizontal direction. Now, if what RHIC predicts right, then I should see more particle or large particle momentum along this vertical direction and smaller particle momentum along the horizontal direction because the particle try to escape along the short axis here. But the first movie I want to show you here, this is just tell you. So basically, the dashed line here indicate where's my target, and this small dashed line circle rectangular there show you the shape of the cross-section of my jet. The first movie I'm going to show you here is what happens if you use a big particles, 1 millimeter size particle. Remember, for 1 millimeter or bigger particle, you should see particle behavior instead of fluid behavior, right? So this is what do I see. If my jet hitting on target, you can see even though my target has this rectangular shape, but distribution of the particles is very uniform. From the distribution of particles, you cannot see you have this rectangular cross-section. So that means that for particle behavior, indeed, it doesn't matter what's the shape of the collision zone. Now the next one is the most interesting one. What happens if you use a small particle? Here, you should be able to see fluid behavior. And this is the result. So when the jet hitting on the target, you can see a really big jet shooting up, and there's another jet shooting down, but because the holder here cannot see the another part, this already clearly shows that indeed you have a strong particle flow along the short axis of your cross-section. And if you play this even longer, you start to see this elliptical shape. That's just to indicate that the particle momentum along this two directions actually is larger along the horizontal direction. Indeed, the particle try to escape this area along the short axis. Let me summarize this part. So with the particle, big particle, you see uniform distribution of a particle trajectory. And with small particle, you begin to see this beautiful fluid-like structure. And furthermore, we can change the shape of our slot. So basically change the shape of the cross-section of our beam. You can see when I use a really narrow beam cross-section, I see very strong anisotropy in the flow behavior. And I can quantify that by measure basically second Fourier coefficients of the particle momentum distribution. And I found this mu2, the second Fourier coefficients, is between 0.25 and 0.2. Actually, this range is exactly what RHIC found. They found exactly the same degree of anisotropy in their flow. As I said, this is a really universal fluid structure. And there's another interesting system actually showed a similar behavior. This is the only three systems I know: my system, RHIC system, and this system. This is an ultra-cold atom system. Where they have is they have a trap really cold Fermi atoms. So the temperature here, I think, is 10 to negative 5 K. So what they have there is that they hold the Fermi atom into this cigar shape with an optical trap, laser trap. And then they're going to release the trap. When they release the trap, you see the particle actually expand more along the horizontal direction, along the short axis of this trap. And that's actually identify the Fermi atoms also show liquid behavior. Okay, so let me kind of conclude my talk. I tell you two, again, very simple, but I think it's very interesting experiment. One is a granular impact cratering by liquid drops. The other is granular jet hitting a solid target. And in this two experiment, I demonstrate a lot of transitions between different phases of granular matter. For example, they transform from a liquid state to a particle state, from liquid state to a solid state. And more interesting result from these two experiments that I show you, we can use granular materials as a model system for a lot of interesting physics phenomena. So finally, I want to acknowledge a lot of people. Again, the granular impact cratering is really a new project we initiate. So all the research actually done by undergrad students in my group. And we submit a paper, but if you want to see the paper, we put the paper on archive. And this granular jet experiment, most of the experiment actually done when I was a PhD student at University of Chicago. So I need to thank my two advisors, Nagel and Jaeger. But we do more analysis in this year, so we publish another paper this year. The interesting thing is this: when we try to submit this paper to PLL, we got 5 referees. 3 of them is from granular physics, and 2 are from RHIC. Okay? When we got the referee report back, all the granular people said that your granular jet there is beautiful, but don't make the comparison. Your comparison with RHIC is silly, right? That's an extreme quantum limit. Everything is a classical particle. Don't make this comparison at all. But the 2 RHIC referees say, this is so beautiful. Okay? So really demonstrate what happens with the classical particles. And then we argue with editors saying that, RHIC people, of course, they are right people to make the judgment. and also later on, when the paper come out, the RHIC actually asked us to write a news report for their website. So we have that on the RHIC. So with that, thanks for your attention.
All right, thank you for a really interesting talk. Are there any questions? Yes, and if I could remind you all that we have to have the microphone because this is being recorded.
Thank you. Very interesting. But you said that it's a very nice vehicle to study fluid mechanics. What's the advantage over just using fluids?
Of course. Yeah. For example, I can give you an example for this granular jet, right? For fluid, it's really hard to make a jet with non-circular cross-section. Because surface tension is so strong, you always try to retract the cross-section of the jet to a circular shape. And the big advantage we have here is we don't have surface tension. It's a hard particles. Yep.
Well, first of all, thank you for an absolutely wonderful talk.
Thank you.
So I have a question related to the first part of your talk. And it has to do with the scaling when you compare what's happening at with an asteroid and also with the water cratering. Mm-hmm. There's no mention about the material that, in a sense,
yep,
that you are where you are creating the crater.
Yep.
And may I suspect that that maybe in 2 cases, in this kind of a scale way, the dissipation associated with the fracturing of the material is very small compared to another one.
Yep.
And then I'm wondering that if you were to do an experiment, not using glass beads, which as a system characterized by very small friction angle, mm-hmm, you'd be doing experiment with very coarse angular sand, mm-hmm, mm-hmm, which is characterized by high friction angle.
Sure.
Would you have, okay, maybe the same scaling law, but maybe everything would be...
Yep. So one thing we do, we didn't try rough sand yet. We tried different size of particles. But one thing we know will change the scaling is you put attractive force between particles. So for example, you put some little amount of mineral oil into your bed, so the particle has some capillary interaction between beads, then the scaling will change. And regarding to the asteroid impact cratering, and when they do experiment, actually they do experiment to try to test how the asteroid size crater depends on impact energy. The way to do that, they have this national facility at NASA. They actually can shoot a solid ball at, I think, 10 kilometers per second. And not only that, they have this huge centrifuge. They do that at 500 G. So at 500 G, shoot ball at 10 kilometers per second. Okay, so they found that indeed, the scaling will depend on what materials you have. There are actually two limits. One limit is what I show you here. You have granular particle, there's no attractive force. All the energy actually just move particle out. There's another limit, it's called the materials limit, where the most energy actually is used to break up the materials. You have to input tons of energy. For example, you have a rock, really hard rock, right? The most energy actually break up the rock into small grains first, and then the grain eject out. In that case, you will have different scaling. And the question is why asteroid impact cratering follow the non-cohesive granular case rather than rock case. I don't think they have a really good answer for the asteroid impact cratering community. But they know in experiment, when they do this 10-kilometer impact, they know there will be difference. It depends on how much attractive force you have in your materials. I guess one argument you can have is because asteroid impact energy is so high, actually the energy used to break up the thing is so tiny. Basically everything just eject out. And if you look the Mars and a lot of this planet, actually a lot of parts just covered by desert, right? This is just really kind of a granular surface there. And the good thing for there, especially for Mercury and the Moon, they don't have wind there. So if you just have impact on granular beads, they won't go away. So there's no wind to disturb the surface that the thing will go away. On Earth, actually, if you know the very famous Arizona crater actually also gave aspect ratio of 5, or 0.2 in the direction that I'm presenting here. But most of the Earth crater actually, because of wind erosion, you already cannot measure what's the initial aspect ratio anymore. Yeah.
What happens when you have two components of velocity instead of it always being perpendicular to the...
You mean the jet or the liquid?
Well, I was thinking in the impact crater.
Okay. That's a very good point. That's a very good point. So we try to submit the paper first, and then one astronomer doesn't like it. They reject our paper. And the big reason for that is that they say that try to link low energy impact to high energy impact actually slow down their field. The reason why is this. So the first guy who realized that you can use low energy impact to mimic asteroid impact, actually Coulomb law, right? That's the early 18th century or something. And he do a very simple experiment. He drop a ball on a mud or on granular surface. He sees a crater, and he see, oh, this crater looks really similar to the moon crater, and the moon crater probably is because of impact. And then the end of 19th century or early 20th century, people suddenly realized that if you have a ball coming from a certain angle, like what you asked, you won't get a circular crater. You'll get an elliptical crater, okay? But on Moon, 96% of crater is a circular crater. And it's ridiculous to say that all the asteroid impact happens exactly at normal angle. And that's a big argument there. Then people say that, oh, the craters on the Moon actually is not from impact. It's some geological process like a volcano, earthquake. That's how you can have those craters. And that slows down their field a lot. That's his claim. And then later on, people realize that actually if you go to really high energy, like a 10 kilometers per second, that's what they do in NASA, the impact happens is inside of like an impact cratering is more like explosion cratering. So a small asteroid actually can generate a really big crater. If that happens, actually the angle doesn't matter, even the shape of the asteroid doesn't matter. You always can have a circular crater because it's essentially like you deposit energy to one single point on Earth and then create a big crater. But we don't do the experiment from the angle yet. I'm sure that if I do the angle, I will get elliptical shape of craters.
Maybe I can ask a little question.
Sure.
It seems like one of the controversies within what might be called the granular physics community is whether or not you can really say there's a granular liquid. That especially maybe
Yep.
people from the kinetic theory background might say that.
Yep.
And they give various justifications saying,
Sure.
for example, a liquid has surface tension in granular materials.
Yep.
But clearly you make this statement that in at least, maybe you don't say it's a granular liquid, but you say it behaves like a liquid.
Yep. So
okay.
sorry. So yeah, this is a good point. I should emphasize, I say granular liquid specific for this geometry, for this system. And one reason why this one behaves so good, like a large Weber number water, right? Your water result, is because the momentum transfer is so fast. If you have a slow granular flow, then you really need to consider about what's the viscosity in this case. right? How the momentum transfer, what's the transport coefficients in granular flow. In that case, the property will be different from Newtonian fluid. And the reason why here is behave really like water at high Weber number limit because my momentum is really high. So I actually, my jet impact on target at 10 meters per second. I'm not sure whether that answers your question.
So I guess my question is, what makes a liquid in this case? And it seems like what you're saying is it has to have, there's some memory of a previous collision. Like maybe your liquid is similar to what, maybe a dense gas, but the important part is having a memory of previous collisions. Would you say that that's what?
Sure. So when I say liquid here, I think that one point you're right, that I cannot distinguish a dense liquid. So actually it's a fluid. I would say use the word fluid instead of liquid, because I cannot distinguish gas and liquid. I don't have surface tension here. Everything just a smoothly increase, right? So if you see the plot I show you here, this is really just a smooth transition. I don't see any sharp transition that above that I can call that liquid, below that I can call that gas. So it's really we can say that's a fluid-like behavior. Okay, good.
All right, thanks. Let's take our
Thank you.